Now we are in linear transformation topic. There you have a kernel of t. What is kernel of t? T from V to W is a linear transformation. It is kernel of t is defined as u belongs to V. That means you have to take an element in V, that is u. Then t of u is equal to 0 vector in W. 0 vector in W. If this condition is satisfied, then your u goes into your kernel t. If that condition is satisfied, then your u goes into your kernel t. Which condition? T of u is equal to 0 vector in W. T taking an element in V goes into W. In W, if it is mapped to 0 vector, then that u which is present in V goes into your kernel T. This is the definition of a kernel T. Let us deal a theorem based on this kernel T today. Statement: let T be a linear transformation from a vector space V into a vector space W. Here he has given that T is a mapping from V to W, which is a linear transformation. He has given that. Then you have to show that kernel of T, or it is said to be a subspace of T. Then we have to show that kernel of T or subspace of T is a subspace of V. We have to show that one. So, go to theorem. First write what he has given. Given T from V to W is a linear transformation. Here LT is nothing but linear transformation. Shortcut rasanu. Let 0 vector in V, 0 vector in W be 0. Vectors kabatti ikkada bars pettesaru. Since it is a vector, you have to mention it 0 vector in V, 0 vector in W, be the 0 vectors of V and W respectively. Then we know that T of 0 bar V is equal to 0 bar W. This you have seen in a note after linear transformation. I have given 2 notes there. In that this condition is present. So that's why I have written we know that T of 0 vector in V is equal to 0 vector in W. See, T of 0 is mapped to 0 vector in W. This is the condition satisfied with kernel of T. T of some element goes into 0 vector in W, then your u is present in kernel T. Then T of 0 vector in V is equal to 0 vector in W you got, then this element goes into kernel of T by the definition of kernel. By the definition of kernel, this 0 vector in V belongs to kernel of T. Then I can say that one element is present in kernel of T. That's why we say that therefore kernel of T is a non-empty subset of V. That means it is containing some element there. After that, now going to the main part of our theorem. Now we have to show that kernel of T is a subspace of V. To show it is a subspace, 3 conditions should be satisfied. That is, first one is 0 vector belongs to kernel of T. Second one is u plus v belongs to kernel of T. Third one is cu belongs to kernel of T. Going to the first, 0 bar belongs to kernel of T. From 1 you have already 0 bar v belongs to kernel of T. Here first condition is satisfied of your subspace. Going to your second point, u plus v belong to kernel T. For this you have to consider 2 elements. Let u comma v belongs to kernel of T. I am saying that u and v are present in kernel T. That means it satisfies this condition. T of u is equal to 0 vector in W, T of v is equal to 0 vector in W by the definition of linear transformation. This one, sorry, not linear transformation, kernel. I am saying that u comma v belongs to kernel of T. Kernel lo undi ani cheptunnanu kabatti it satisfies this condition. T of u is equal to 0 vector in W, T of v is equal to 0 vector in W. Now consider T of u plus v. Now consider T of u plus v. That is equal to T of u plus T of v. This is by the definition of linear transformation. This is by the definition of linear transformation. T of u is nothing but 0 vector in W. T of v is nothing but 0 vector in W. 0 vector plus 0 vector you will be getting 0 vector. Now again see here T of something is equal to 0 vector in the W. That means this element goes to your kernel of T by the definition of kernel of T. So you got the second condition also, u plus v belongs to kernel of T. U plus v belongs to kernel of T. Second condition is satisfied. Now let us go for third one. We want u belongs to kernel and c is any scalar. So let us consider u, c be any scalar and u belongs to kernel. Now consider again T of cu. T of cu can be written as c into T of u by the definition of linear transformation. This one, c into what is T of u? T of u is 0 vector in W, 0 vector, substitute this one. Then 0 vector in W, something into 0 you will get 0 only. So 0 vector in W. T of cu is equal to again 0 vector in W vachesindi. Ante this is satisfying the condition of kernel. That means this cu belongs to what? Kernel of T. Cu belongs to kernel of T. So we have showed 0 vector belongs to kernel T, u plus v belongs to kernel T, cu belongs to kernel T. So all the 3 conditions of the subspace has been satisfied. Therefore I can say that kernel of T is a subspace. Finish.